Today I'd like to complete the broadcast channel chapter, and then we'll move on to multiple access channels. So let's just start with a quick review of some of the things we talked about yesterday. So if we were looking a lot at the broadcast channel, where we have an encoder that sends one sequence of symbols. Again, the sequence can represent a waveform. It can represent a band-limited waveform. It can represent a non-band limited waveform. It's basically, again, it's a representation. Usually we represent signals, let's say in L2, by a linear combination of basis functions, right? So these are just those parameters that are there. And then we have a channel that maps these symbols to output symbols. Y1, Y1, Y2. So here we're looking at a 2-receiver problem. Of course, a more general version has 3 receivers, or 4 receivers, or what you have in practice often, of course, 20 receivers in this room. So all these problems are interesting to look at in that context. Oh, and now I have to say what we're trying to transmit. So in general, we have a common message that we're broadcasting to both receivers. And there's 2 different estimates, but we were looking at the more general version of the problem, which fits also wireless communications or cellular communications better than, let's say, radio transmission, where usually you have the broadcasting in the usual sense. So this is a more general broadcasting. And that's the problem we were looking at. And we were asking for the, this is all have different rates, R0, R1, R2. And so we're looking for the set of rate triples, R2. That's what we're looking for. And the capacity region, we said what we're really looking for is a region. This is R1, R2, R0. We're looking for some region that looks like this. And yesterday, first thing we looked at was the boundary point where R1, R2 are 0. We were able to find the capacity of that problem, where we said, well, that corresponds to a compound channel problem, where, well, first we said the capacity region depends only on the marginals. And because of that, it's equivalent to a compound channel, where either we get one channel or the other, and we're asking what is the best thing we can do if we don't know which channel it is and we still have to send data. So that's called a compound channel. Then next we looked at another, so that coding was quite easy. Then we looked at another situation where we were operating in just the R1, R2 plane, and we came up with the first new coding scheme, this Martin coding, or sometimes nowadays called multi-coding, where the idea is at the encoder we generate code books U1N that are too big and U2N. So these are too big in a way, right? This is the extra size we give, right? So that we enlarge the code book for both the user 1 and 2. If we didn't enlarge them, they could just be regular code books, right? So another way of doing this is just to say, well, this is the output of a low-density parity check code. This is the output of another low-density parity check code, which is just BPSK, and then we just add them up, right, after weighting them with different powers. That's an easy way of doing things. That's called, well, okay, that's superposing the two. Here we're doing something more sophisticated. We make the rates lower in the sense that, well, or rates higher artificially, I guess. We're enlarging the code book. So it's like adding more bits. So these are the message bits. Now we add more bits. Some of the bits are reserved to ensure that when we generate the code words, we find a pair so that these are jointly typical with respect to some constraint. So they're matched somehow in some way. And we discovered that the rate, if this has rate R1 primed and this has rate R2 primed, that what we need to accomplish that is that that's bigger than U1, U2 if that's the typicality we're looking for, where this was generated with the probability of U1, probability U2, and we chose a joint distribution for them. Anyway, so that led us to a rate region that looks as follows. R2, the first one has I, U2, Y2, that's not surprising. We would achieve that even if we didn't do this, so if we just superposed the code words, like LDPC code 1, LDPC code 2, add them up, we would get this anyway. Same thing here. And normally, if we're coding independently, we would get that corner point. Right, so if this was statistically, if these were statistically independent, this would be 0. Then we would achieve that point, but now we back off on the rates, right, which sounds like we're making things worse, but what's actually happening is these points move out, and we get a bound coming in. And this bound coming in has the following form. The amount we lose here is exactly that mutual information, right? So this gap here is exactly this I, U1, U2. And it's the same gap here, right? This gap here is I, U1, U2. Right? So what's effectively happening is we're hoping as we add correlation, these two move out faster than that thing coming in, right? And if that happens, then instead of getting a region that looks like this, I should be a little bit careful. Instead of getting a region that looks like this, right, we get a region that looks like this. And that sometimes happens, right? Because sometimes it's important to align these vectors. Okay? So that's the region we get. We discussed about getting to the corner points, right? So then we talked, the corner points are always the first interesting objects to look at, because they tend to give a lot of insight. And so we looked at this corner point, and then if you look at that rate, you realize, oh, that's IU2, Y2, but this rate here is IU1, Y1 minus IU1, Y2, right? So at this corner point, that's marked. I know it's dark. But I'll just write it like this for now. U1, Y1 minus IU1, U2. IU2, Y2. Then I'll stop using this color. So the main point here is we're viewing this U2 as state, right? So, and if you'll remember, for the Gelfand-Pinskrift problem, we had IUY minus IUS. Right, so it's like the interference. And so you can actually operate at these corner points by building a dirty paper coding method. And that's why there was a lot of interest in building stuff like that. And as I mentioned, there's ongoing work on that even today. There's still not a really, I would say, really nice kind of design for coding for the dirty paper coding problem. Some people might disagree and think their design is a really nice design. That's usually how things are, right? But I think nothing that's really would make it into practice yet, I think. But people are working on this. I know there's been, as I mentioned yesterday, there's publications that came out on arXiv, I think even in the fall of last year, from researchers at Bell Labs who are publishing on this because they're interested in doing something on this topic. And I think that's an interesting direction. The key is to try to find a simple method. Okay, so that was one thing we looked at. Then we looked at a second coding method, which we called superposition coding, which, as I said, was a little bit more straightforward in a way. Effectively, what we're doing is we generate one set of code words, UN. So here, we did this for the, what we did is we said, okay, we'll generate one code word that carries, let's say, the common message, a common message. We actually also included the second message on this, W2. And then on top of that, we stack a code word that has this pair in it, but also includes the extra message meant for user 1. And what we decided to do is have user 2 decode only this U piece. So the idea is decoder 2 decodes only this. And decoder 1 must decode everything, right? And it turned out there were two bounds that came out of that. One was this, x, y1 given u, and r0 plus r2 plus r1 plus r2 less than or equal to ix y1. So that was the region we got there. So I mean, if I plotted it just with r1 and r2, so let's just do it that way. Let's just take out the r0 so we can plot it like here. r1, r2, guess, yeah, r1, r2. Then we'll again get a pentagon of some kind in general, right? We'll get an r2 bound, which is the same as over here, iu2, y2. And here we'll get a different rate than this, namely ix y1 given u. And then in general, you have this thing coming across here that intersects these boundaries at ix y1, right? So the new region that we get is the orange region. And then what we did there yet too is we said, okay, we'll look at a special class of channels now for this, because what's interesting about this strategy is what we have is user 1 is, receiver 1 is decoding everything, right? And then throwing out, just dropping these 2 bits, right? So, but it just decodes everything. And throws out some bits. That's okay for us, right? Because we're not interested here in, say, the security of these bits. We're just interested in maximizing transmission rates. Right. And those kinds of, that kind of setup where user 1 decodes everything is interesting, especially in for problems where user 1 is better than user 2. So then we came up with this idea of degraded channels, where we say a channel is degraded if it has the same marginals as a broadcast channel that is physically degraded. So same marginals as a BC that has x, y1, y2, right, Markov. So that this chain is Markov. So then it's physically degraded. And we use that to show that, first of all, this bound isn't needed anymore for degraded channels. So we just wind up with these 2 bounds. So effectively what happens is this bound is a higher up than what we have is the funny situation where this looks like this, and this third bound is somewhere out here, right? So it just becomes a rectangle. And then the optimization is just, you know, taking the union of all such rectangles, so we get a rate region. Just drawing it very quickly. Sorry about that, I could draw it more slowly, I guess. So we get R1, R2. So we get these 2 bounds, IU, Y2, IX, Y1 given U. And so we get a rectangle, and then as we change the statistics, these rectangles start looking like this. So you might have a region that looks like that, right? And we discovered that this is in fact the capacity region for such channels. And it should make sense somehow, like intuitively, because Y1 can decode everything, so it makes sense to have that guy decode everything. And this guy here is you know, can send something less. Still, I mean, coming up with this strategy is kind of interesting, right? It's an information theoretic approach, and then after you do the information theory, you try to interpret what the code means rather than the other way around. So this is Tom Cover's paper from 1972, this is superposition coding. It's probably the most practical way of coding for broadcast channels, and it's optimal in some cases. But for some cases, you know, this one is optimal, as we've seen, and there's no case, I think, that we know of. We don't know whether the combination is optimal or not, or if these 2 are enough. But That's the situation. So we did some examples with Gaussian broadcast channels. So for the additive white Gaussian noise broadcast channel, where y1 is x plus c1 and y2 is x plus c2, where this object here has variance sigma 1 squared, and this object here has variance sigma 2 squared, where sigma 1 squared is less than sigma 2 squared. That's an example of a degraded broadcast channel for which we get the capacity region with this strategy, and all random variables are chosen to be Gaussian is the best thing to do. So we did a lot of examples and some details on this problem. So that leaves maybe one last thing to do. First of all, are there questions about that? Right. So this concept of degradation extends naturally to 3 receivers, right? We could have a Markov chain with 3, for example. The capacity region, again, depends only on the marginals for those problems. Again, degraded, channel would be called degraded if it has the same marginals as a physically degraded channel. For physically degraded channel, there's a natural extension of this. All we do is we stack, we call this U at the base level, we call this U at the next level, and then we stack X on top. The X is really just another level, right? So I could have just called it, let's say, U naught and U1, right? And so you can continue stacking up this stuff, right, if you wanted to, and that's how you could deal with many receivers. And then every one just decodes everything that comes, further back, right? So this guy can decode everything, this guy can decode everything except for that extra piece, the last piece, and so on. And that turns out to be the capacity region for that problem. And Bergmans wrote a longer paper on this around 1974 or 3 as part of his PhD thesis to show that. And then prove that for Gaussian channels, Gaussian distributions are optimal, and all that, right? I mean, these are usual thing, you have an idea on your PhD, and then you generalize it, and finally you wind up with 100 pages, and you finish your PhD, right? That's how it works. Hopefully you have 1 or 2 ideas, and 1 or 2 ideas should be enough, right? It's hard enough to get one good idea. Questions? Yeah.
So in which cases margin coding is optimal and in which cases superposition?
Well, so we discussed a few examples. Superposition coding is optimal for degraded problems, but there's other classes for which it's optimal, which I haven't discussed. One of them is called less noisy. So there's generalizations of this idea of degraded. One is called less noisy, and one is called more capable. Or less capable. I don't know why these words, there's sort of historical reasons. I think whoever wrote the paper just happened to think whether more is better than less or less is better than more. I don't know. So there's a class of channels called less noisy, and then there's a class of channels called more capable. We could have called them more noisy and less capable, or more noisy and more and so on. But anyway, this is the most general class. This one includes this, and this one includes degraded. And for this class also, superposition coding is optimal. Okay, but as we saw yesterday for deterministic broadcast channels, this will not get capacity in general. There's classes where it doesn't, whereas this does. Okay, and there's classes where, for these classes, like for additive, well, for the Gaussian channel it works, but I'm quite sure, I made that statement yesterday, but I'm quite sure that Martin coding will not achieve capacity for binary symmetric broadcast channels. It does for Gaussian channels, as we saw, because of this remarkable fact that with Gelfand-Pinsker coding, you can get rid of interference. But that's only valid for the Gaussian channel. As soon as you move away from Gaussian, it's usually not true. And so that already shows you there's problems where this method is best, and that is strictly suboptimal, I'm quite sure, and vice versa, for sure. Like for deterministic channel, this is optimal, but this is strictly suboptimal. So that tells you we're missing something, right? Or maybe there's a way of pasting these two together to get the best performance, and that is today what the best coding method is. It's pasting these two together. So I can describe very quickly how that pasting together works. But it's not so nice. It's really just taking one idea and another idea and kind of putting them on top of each other. So it's not, for all problems, so that's the best known rate region. Maybe I can write that out now quick on what the best known rate region for the broadcast channel is. It's really a combination of superposition coding and Martin coding. The idea is quite straightforward once you know both of these ideas. I mean, all we're going to do is the following. We'll generate a base code word, u, let's say, I think I called it in the notes, for some strange reason I called it t. It's probably historical. Tn, and that's going to carry the common message, Tn. So maybe here I can introduce one more thing. So let's look at, let's say generalized Martin coding. So this region first appeared in the textbook of Cesar-Kerner, I think, although it probably was known in the community before that, I'm guessing, or thought about it, because it's sort of straightforward once you know all this stuff. This stuff was done by, I think, by Kerner and Martin, these two pieces. So if we generalize the coding, what we do, well, let me describe it first in its basic form, and then I'll add how you can slightly enhance it. So we code using PT. So we choose a joint distribution with 3 auxiliaries now. And the reason for choosing 3 auxiliaries is because one should be for the common message that's decoded by everyone, that carries information decoded by everyone. This carries information decoded only by user 1, decoded only by user 2. Okay? And so we put all the common bits into one code word. Later I'm going to add some more bits to this. That's why I draw it a little larger. And then all we do is on top of this, for every W0, we do a Martin coding. Okay, and that's all it is. So what we have here is then going to be a U1N with W0 and then 2 indices, W1, V1, right? If we didn't have this, it would be pure superposition coding, right? And now we're just making code book larger. We do the same thing here. And then these two are generated independently. So we generate U1 from T on top of T. We generate U2 on top of T, but independently. But then we do this trick of searching for a pair V1, V2 so that they're actually jointly typical. That's the whole idea. And then what we need to have, if this is R1 primed and R2 primed, is that R1 primed plus R2 primed has to be bigger than I U1, U2 given T. Which makes sense because we're just going to do this across all, you know, we can collect all letters T and then it just becomes an average. And that's the main trick. So it's sort of just a pasting together this idea and the Martin coding, and then of course we've included both, right? So that's a way of generalizing, but it's not such a deep generalization, right? I mean, the depth is really already here. So let me add here, we choose this U1T, we choose this U2T, and then we do the combining step. And if you put this all together, there's one extra trick we can do. Let me add that, I'll mention it quickly. It might make sense to take some bits from the first message and have both users decode them, right? And it might make sense to take some of the bits of user 2 and have both users decode them. And so this is another generalization. So this is called rate splitting. So we can add that too. We'll see this rate splitting idea appear for the multiple access channels too, and also for interference channels. So the rate splitting is we say split the message W1 into 2 pieces, W1 primed and W1 double primed, and split the message W2 into W2 primed, W2 double primed. And then we'll stuff some of the bits into here, just to make everything more complicated, right? And that's it, right? And here this would be split and split, right? But otherwise everything works the same way. But by doing this splitting, you can sometimes make things a little nicer and rounder, and sometimes it actually even improves things. So if we put this all together, we get a very big rate region, and we do Fourier-Motzkin elimination and all these primes and double primes and so on. So it takes a little bit of work to put it all together in the right way. And finally, we wind up with a region with 5 bounds, and it looks as follows. I'll just write it out. So we can achieve the following rate for a given joint distribution. And of course, we can add a function from which we get x from that, but it looks as follows. just for to show you how frightening this all gets very quickly in terms of expression. So it takes some time to understand the meaning of these things, of course. So those two should be intuitive, right? User 1, after all, decodes the common piece and its own, right? So that's basic. These two bounds are quite basic. Then comes two sum rate bounds. Namely, this one's a little harder to understand, and I don't know if it's so easy to explain these things, but u2, y2 given t, and here's the loss, u1, u2 given t. So this here is due to the binning, right? That piece is that reduction in rate because we want to make these correlated, these u's. Right? That's this. That one's easy to understand. Here we have the first rate. That will be R0 plus R1, and this one will be kind of an extra rate due to R2 in some sense, right? So this is the loss, these two, and this is some extra rate to user 2. So maybe it's not so hard to interpret. And now we get the same bound, just symmetric, just swap the indices u2, y2 plus I of u1, y1 given t minus I, so it becomes symmetric, u1 given t. And here's the funny bound. There's a funny looking bound, 2r0 plus r1 plus r2. And I'm just writing it in the way I like to write it. There's another way to write it, but this region. But anyway, this is the one that's clearly the larger version, although you can show it's not really larger. But anyway, there's another way of writing this with an R0 bound rather than this one. But this is then you would get two extra bounds rather than one. Anyway, so it looks like this, right? So if we plotted this now, we would, have this rate region. We would start every one of these. If you look at the bounds we have, it's kind of going to be hard to draw for me. These are all different planes, right? This bound is a bound on R0 plus R1. So if you think of what that is, that's kind of like a diagonal bound like this. It's kind of like a plane that's in here. So in this plane, it's just a diagonal bound, but it's like a sheet, right, that comes out in this direction. Right, it's a bound like that. And then similarly, the second bound is a bound in this plane, so it's like a sheet that comes out this way. Then we have a bound that comes out, it's 45 degrees here. And then we have a funny looking bound which is sort of tilted, or tilted like this, actually. I guess it goes, I'm not sure which, it weights R0 a little bit higher, right? So I think it goes out like this a little bit further, something like that. Anyway, so the combination of all these bounds, and then we take the union over all joint distributions, and that union will then become generally a shape like this. And for all channels for which we know the capacity region, this is the capacity region, that union. For all cases which we know of, that we have a converse bound that matches the achievable rate. This is the best because it combines all the methods we know. Right? Rate splitting, superposition, Martin coding, combines all things in one. And again, yeah, every case, there's no other rates that are known that are better than this region. Now there are simple extensions where you can, conceptual extensions to improve this. For instance, we could code over 2 letters at a time. Like suppose we use, instead of looking at every individual letter by itself, we take pairs of letters and then view those pairs as a letter. Then these all become vectors of length 2, but of course we have to divide by 2 because we're using the channel twice. But still, potentially those can improve rates. But it gets complicated as you can't believe, right? Those aren't nice extensions to do that. Okay, so we always like to work with single letter expressions because we want this sort of independence over time in deriving our rates. Okay? So anyway, that's the state of the art today in terms of basic bounds for broadcast channels. And it's been the state of the art since 1980. This hasn't been improved. right? The only thing that's improved is people have found better upper bounds to show that this is the capacity for some problems. But there have been no improvements in coding methods in the last 35 years for this problem. And that's why also I think some people like to believe that, you know, you sometimes hear this, oh, you know, many smart people worked on it, you can't improve it. Well, who knows, right? I mean, maybe everyone is just missing something simple. Okay? So again, all the improvements have been on upper bounds, not on lower bounds. At least on the level we're talking about. Of course, you still have to optimize that union. That takes hard work, so showing what is optimal. But the structure, the architecture of the coding, this is the best known method still today. Okay, so that was just a half-hour review of what we did yesterday. So let's go to the next problem. So we've been talking about so broadcast channels is like base station to mobiles. Now we'd like to talk about the other direction, mobiles to base stations. So this is known as a multiple access channel. Or MAX. Okay, so we're just going to turn everything around. Suppose we have two transmitters now, encoder 1 and encoder 2. So these are two user equipments, two mobile stations. This one is sending X1N. This one is sending X2N. And we have one channel that takes in two inputs and puts out one output, which is the base station's output. We have a decoder, and the decoder has to put out the messages. Let's suppose first of all, there's two messages, W1 and W2. This one has NR1 bits. This is NR2 bits. And the decoder puts out these two estimates, right? And the problem is to find the set of rate pairs for which we can communicate reliably. Now I'm going to do something funny. I'm going to add a third source, and part of the reason is to somewhat make this a bit more symmetric with respect to the broadcast channel. And I'll explain why. You'll see a little bit why I'm motivated to do this later on, but I'll add a third message that goes to both. This just might sound a little strange, right? I mean, but I'm sort of trying to mimic the broadcast channel, and by doing this, we'll be motivated to do something that's a good idea to do, and that's why I want to do it. So let me look at the generalized multiple access channel problem. If there is no message, you can just make that a rate 0 object. Okay. Now, so the problem is to find the set of, and we'll be mostly interested in R0 equals 0, as you'll see later. Find the set of rate triples for which we can communicate reliably. So I'll just shorten this error probability statement. Communicate reliably. The closure of this set is called the capacity region, CMAC. So again, the region will look also again like what we saw before, R1, R2, R0, and we'll again get these regions, right? It's the same idea, right? I mean, again, we're looking for a three-dimensional region. We'll focus mainly on the case R0 is equal to 0 in later. But first a comment about this channel model. Because we have two transmitters sending data and one receiver receiving, there is a subtle issue that if you're thinking of waveform communications, you know, there needs to be some kind of synchronization here, right? Like if you're thinking of this representing a band-limited signal, somehow, you know, we're sort of assuming that this thing here is synchronized with this so that the ith letter here is a noisy function of the ith letter here, and so on. So there is an issue of synchronization, and I emphasize this for the following point. So there's issues. You know, synchronization. Is sort of assumed here. So these are practical issues to think about when we try to relate this to channels. We can say this is actually okay for band-limited signals. Although even there, what I mean by okay is open. What I mean is actually, it turns out that, so if we didn't have the common message, even if they weren't synchronized, the signals in some way, you know that if you sample a band-limited signal anywhere at the Nyquist rate, it doesn't matter where, you get a full representation of the signal. So even if this is shifted in time by half a symbol, you know, no problem. The only thing we'll have to do is when we do decoding, we'll have to worry about that, you know, perhaps resampling to shift the signal. So we'll have to do some kind of interpolation potentially on the signal. But that's okay. Those are points that you get to when you try to figure out how to map the continuous time model to this, which is an interesting problem by itself, right? So I mean, here we're just studying the abstract model, but it's really interesting to think about how real waveform models, you know, map to this. That's an interesting question. Okay, so I just emphasize that. And now I'll get to the point why I introduced a W naught. I'd like to have this common thing represent the fact that we have a common timing base for both transmitters. So for example, it might be just a GPS signal, right? So both transmitters have this common time. Okay. So W naught for us will represent, I mean, more generally it represents a real message, but for the case we're most interested in, W naught equals 0, that still says there's a little bit of information on timing. And this timing is important here to permit time sharing, of course, or frequency sharing, and so on. Okay, so questions about that model? Because once we have the model in place, we just continue as usual, right? So now we'll build codes for this. And it turns out that the right way to code for this problem, you don't really have a whole lot of choice. It's actually just superposition coding is going to be the right thing here. If W naught was 0, it's kind of almost obvious because x1 and x2 then have to be independent given the timing. So there isn't much more you can do like Martin coding or anything like that for this problem. Okay, so let's do a code construction. So what we'll do is we'll choose an auxiliary random variable again. And the reason for the auxiliary random variable will be the common piece. So we'll choose a PU, and then we'll choose a PX1 given U and a PX2 given U. So, right, we can't, because of the structure of this diagram, if we're given this W naught, X1 and X2 have to be statistically independent, right? Because this is just a function of this, and this is independent of that. So that's why I'm choosing this structure here. This structure causes us a little bit of problems later and has led to some errors also in textbooks, which had to be corrected later. Like these things are, when you have Markov chains like that, it's a little tricky because the set of these distributions is no longer a convex set, right? And that's fundamentally what, you know, sometimes you have to worry about that a little bit. But still, it won't prevent us from solving the problem. And now what we'll do is build a code book like this. So I won't describe it in words anymore. I'll just draw pictures. So what we'll do is we'll generate, using PU, I'll generate the U code book, UN1 to UN2 to the NR naught. Okay, and then on every one of the code words in this code book, I will stack 2 further code books, right? One code book for encoder 1 and one code book for encoder 2. So what I'll do is I'll generate another code book. Here, x1n indexed first by 1 and then 1. and then x1n1 2 to the nr1. And at the same time, I'll stack another code book, which I generate independently. So this one's generated via p x1 given u, where again we look at every letter here and then generate the first one by conditioning on this symbol, then second symbol, third, fourth, and we'll repeat that for all these, right? Same way we generated before. And similarly for the code book of user 2, xn 1, 1, x 2n 1, 2 to the n r2, right? So and then we do this for all code words. That's the idea. So it's pure superposition coding. So this is pure superposition coding. Okay. So now maybe a word on that quickly, historically. So historically, this problem was first looked at without this. And if you do that, of course, you have no superposition coding. And I emphasize that because, you know, Shannon already in his two-way channel paper at the end of the paper writes, you know, we have a complete theory for this channel model. This is his course notes at MIT from 1960. In his two-way channel paper, but I've was shown course notes from Shannon's course at MIT back around 1960 or 61, where the person who was in the class drew out this channel, and also you could tell Shannon knew what the answer was for this problem. Okay, but he never published this, and the first publication of this was then by Alsveda in 1972. So, and there was also a paper by Liao, his PhD thesis from University of Hawaii, around the same time, but usually Alsveda is credited with first solving this problem in published form. There, Alsveda didn't have this, so there was no superposition coding going on there. Okay, and so then there was a lot of activity in the 1970s to look at these problems because people were started to get interested in network information theory. Alsveda had already solved the problem. This more general version with a common message was first done by Slepian and Wolf again, but in another paper from the early 1970s. Just as a quick comment on the historical aspect. Okay, so now what does the receiver do? Now the receiver, so this is the code book. The encoding is clear. User 1, so encoding user 1 given, so user 1 or encoder 1 given W0 W1, what does he transmit? Well, just that code word, transmit x1n W0 W1, and user 2 similar. Right, just transmit x2 and W0 W2. Okay, so what does the decoder do? Well, the decoder has to decode all three messages, and we'll do it just all in one shot. That's usually the best approach, just one big joint decoding of everything. So given yn, try to find a rate triple either that if you're using a maximum likelihood decoder, you would choose a triple that maximizes the a posteriori probability, or a map decoder or ML decoder. Here we're using typical sequence decoder. And so what we're looking for is something so that all three objects are jointly typical. Are jointly typical, and just to be perfectly precise, with respect to the full joint distribution, u, x1, x2, y. Right? Where, of course, you know, this thing here is written like this. So this factorizes like this. That's the one we plug in here, right? Because that's the one that we have over the channel. PU, PX1 giving you, PX2 giving you, and that. Right? Otherwise, so why do we need to choose this one? Because if we choose anyone else, the correct code word won't pass the test, right? So we need to choose the correct, the one that corresponds to what's actually going on statistically, to make sure that the correct code word falls into this class. Otherwise, we would make a mistake, right? So we have to choose this for that. Fine. Now, the thing is, though, so we could analyze this, and by looking at what the error probabilities are, and again, the usual way to treat these problems is to split the types of errors into all possible classes. How many classes of error events are there here? Well, there's 7 of them, right? Now, you might wonder, why do we need to do this? Well, you could do it directly, but in the end, you'll just wind up with the same analysis, the same results anyway. You can try that, but anyway, to simplify things, we split the error events partition the events into 7 classes, right? So we'll get 7 bounds, 1 bound for every possible error event, right? Just like we saw for broadcast channels. So we consider 7 possible error events. And these are all disjoint, of course. Error events, right? And well, you know what they are. So let's start with, well, we'll have to go through all 7 of them. And so you can see very quickly that once the number of messages gets large, these rate regions start blowing up in terms of the number of bounds you have, right? So they start getting a little bit difficult to work with, which is why for larger systems you need to do some kind of simplification. The usual simplification that is done today is things like inverse coding to get parallel channels, and then we just live with the interference. But that's, of course, easy to deal with, right? And it's a very pragmatic approach. Still, it's worth thinking about whether one shouldn't start looking at these problems in more detail, and that's actually what's happening today. So in CDMA, interference was treated as noise. So 3G and 4G, you orthogonalized everything to avoid interference, and now in 5G, people have been spending a lot of time looking on this thing called NOMA, non-orthogonal multiple access. Well, that's exactly this stuff. It's just this channel right here. That's NOMA. Right, so people are redoing a lot of old stuff, maybe with a little bit more details fitting to the new channel models, but it's effectively rolling out a lot of old ideas again and looking at them in a more modern context. Okay, so let's look at the error events. Let's start with the first one. What's the easiest one to start with? Well, let's just look at this one here. W naught hat is not equal to W naught, and let's have W1 equals W1 hat. And so this is the first error event. Suppose the error event is that we got those 2 right, but that one wrong, right? And what's going to happen there? You can quickly take a look. Well, what we're asking is, what is the probability? So the probability, this event, suppose this is the error event, the probability of this error event, let's call it 1, is the probability, the event is the union over all possible W naught hat not equal to W naught of the event that this thing here is typical, right? Right? It's just the probability that, well, I guess I should be careful. Maybe the first time I'll write it all out. Then later we won't write it all out. I'll just pointed out on the board. So what's the event? It's that UN, so let me write it big because this is an incorrect code word. Right, so it's the probability, like suppose one was transmitted and suppose all the first indices were transmitted. What I'm doing is I'm looking in another book and seeing what's the probability that the ones here are independent. But these are all statistically independent of what was transmitted because they were all generated independently, right? So all of them are off. So even though this one's the correct one, right, this is the real W1. So if one was transmitted, we're just looking into the next code book, 2 in here, and then checking whether the first ones were typical. But those are on a different subcode book, so they're independent. Right. Y, x1 and 2n, w naught hat, w2, and yn. Element, epsilon typical set. Right. Okay, so this union, we can use the union bound. So what do we get? So we'll get less than or equal to 2 to the n r naught minus 1. Right? That's how many elements are in this union. What's the probability of this happening? 2 to the minus n I of, well, u, x1, x2. Well, all three of them, right? I, x1, x2, y. Right? That's the bound. So the first bound we get looks as follows. I want to keep that, so maybe let's write them here. R naught less than I u x1 x2 y. And since we have this Markov chain, u x1 x2, you know, once we have x1 and x2, they split, because here we don't have a u, right? We may as well drop the u here. This is equal to I x1 x2y due to the Markov chain, right? Okay, so let's go to the second error. We can try this one. What will we get? Same answer, right? Because, well, we're just looking now into the second code word and all the others. But now, of course, we're counting a lot more. This union will now be changed to the following, W1 hat not equal to W1. And now here we'll have the incorrect word, and here we'll have the correct one, right? But otherwise nothing changes, right? Everything here is still independent. Except that the union got bigger, so we get the bound R naught plus R1 less than I x1 x2y. And that's nice because now we see, we can get rid of this bound, right? It's redundant. We don't need this one anymore. This one's redundant. Right? Because if this is satisfied, automatically that is satisfied. Right? So that's good. The same thing is going to happen if I do this. Except that I'll get R naught plus R2. Okay, and what if all three are wrong? Well, now I'll get even more value in here. And now this one is wrong too, and now we still get the mutual information, but now we've taken a much bigger union. In fact, we're going to get R naught plus R1 plus R2 less than the mutual information between x1 and x2, y, right? Which is nice because now we can get rid of both of these bounds too, right? So that's nice. We got rid of 3 error events. The most important one here is the one where all 3 are wrong, because that's the one that dominates the others in terms of the probability of error. Okay? So now let's go to the 4th error event. Sorry, the 5th error event. So we have a 5th one here. Now what we're going to have to do is make this equal and check out the others. Right? So let's make this one and make this one. So what's going to happen? Let's take a look over here. Well, maybe I'll write it out. Let me just write out this event. What's going to happen? Well, the event is going to be the union over W1 hat not equal to W1 of the following situation is happening. UN is now going to be the correct one that was sent. So now we're focusing on this U that was actually transmitted over the channel, right? And that U is actually typical with YN because it's the one that was transmitted, right? So let me write that small. Now we're testing X1. Now X1 it's the wrong one that was transmitted, so we're just testing, was this one here, the second one or the last one, for example, is that happened to be typical, even though it was generated conditionally independent, but it wasn't generated independent of Y, but conditioned on U, it's independent, right? So, but let me write that out. So this is the correct W0, and this is the incorrect W1 hat that we're testing, right? And then if we look at X2N, that turns out to be the right one because we're putting in W0 and W2. And so in fact, the X2N is also jointly typical with YN. So the U, these guys here, U, X2, and Y2N are all jointly typical, YN. Right, that's the event. Now what is the probability of that happening? Well, we already did that. If you think of the statistical situation we have the following. We have P of U X2Y, where we have YN being generated, which was typical. Then we have a UN that was generated, that was typical. Then we have the X2N, PX2 given you, but this one is also typical. And then we have here the probability that PX1N X1N was generated, which is random. Okay, so we can view that as being U and X2 being generated. And we're asking the question, what's the probability that even though X1N was generated statistically dependent on even U and X together, that it happens to be typical, well, conditioned on U, that it happens to be typical of the others. So I guess I could do that this way. I could write it this way if I like. You know, this was generated typically, right? And so I can view this too as a box, and the U is the one that makes them all conditionally independent. Now, do you remember what the probability of that was? So this is just it's the same picture we had before, where we're just viewing this as a vector, right? What was the mutual information? Do you remember what it was? What's the probability that this thing happens? Well, it was 2 to the minus n I of x1 y x2 given u, right? That's the answer, right? Because it was the mutual information between these two given what we're conditioning on. Okay, so it's this. Okay, but let's write this out. We can write this out using chain rule. What do we get? I x1 x2 given u plus I x1 y given u x2. But what is this? That's 0, right? So this simplifies to that. But fundamentally, I should put both in given the statistical test I have. So we get a new bound, namely R1 less than I x1 y given x2u. Right? That's where it comes from, this kind of bound. By symmetry, we get R2 x2 y given x1u. Just repeat everything. And now we have only one event left, namely the 7th event, which is both are wrong. If both are wrong, this becomes a capital. And we get a double union, of course. So this will also add. And what's the statistical situation now? Well, now this one moves over here. Right, now this one is also generated. right? But I can put this all into one, right? Because this is the joint distribution. Like, it's the one that's Markov. Let's just write it out though, like this as px1, x2 given you, right? And now, what am I going to get? Well, I'll just get the x1, x2 on this side, right? That's all. And that's the final bound with the double union. Okay, so putting this all together, I wind up with 4 bounds. Ooh, I'll stop after writing this out. I wind up with 4 bounds. So the following, let's define the following rate region with pu, px1 given you, px2 given you. It's going to be the set of all rate triples that satisfy the following inequalities. 0 less than or equal to r naught, r1, 0 less than or equal to r1, less than or equal to this one, I, x1, y given x2u, 0 less than or equal to r2, less than or equal to I, x2y given x1u, r1 plus r2 less than or equal to I, x1, x2y given you, and finally the rate triple bound right there with just no conditioning on u. Right, so that's going to be the r naught okay, so that is our region, and I claim that the capacity region of the MAC is the union over all these guys of this region. Okay, that's going to be what we want to prove in a moment. So this method of coding turns out to be optimal. In particular, if there is no common rate, you're just generating independent code books. However, you might be willing to have a one sequence here, and that sequence will determine the timing. Like, we can start doing time sharing. For instance, if the first letter here is 0, we might say, oh, only user 1 transmits. If the second letter is 1, we'll say, oh, only user 2 transmits. You know, but time sharing, since it's an average, we don't have to generate it randomly. We can generate it in a fixed fashion. So there's no need to do randomized time sharing. We may as well organize time sharing, and that's usually how it's done in practice, of course. So, but anyway, that's the first, our first accomplishment for max is to say, okay, this region is achievable, and what we'll do after the break is we'll show, maybe I'll do an example first, but then we'll show also that this is the capacity region. We're using standard bounds, nothing fancy, nothing fancy. What will be more interesting will be the examples, especially the Gaussian examples we'll look at.
So the last inequality will be not there if u is not there.
Yeah. So the point that was made now. Suppose if u is not there, yes, yes. But
It will fall back to the fourth one.
No. So if the u is not there, this one will become redundant, right?
Yeah.
But what we'll be interested mainly is in the case r naught is 0. So this will go away. And then if you compare these two, this one here is u x1 y, and that's always bigger than that. So then this bound will fall away. That's what will happen with r naught equals 0. So we'll wind up just with these 3 bounds. But anyway, we'll get there, and then we can remove that one too, of course. That's usually you see 3 bounds on MAC region because there's actually only 3 error events. The W1 being wrong, whereas W2 is right, W2 wrong, W1 right, or both are wrong. So what we did here is just something even more general than that. So we did something more complicated. But my main purpose in doing something more complicated was to show you how this U enters the picture. That was important to me. And I'll explain why, because it turns out that U is important. We can't get rid of it. And the reason we can't get rid of it is because we have this, Markov condition appearing here. So it's important to keep the U. But we'll do some examples of this. Any other questions? Okay, so we'll just